there are three models of light. They are ray model, wave model, and particle model. In ray model, we consider light as rays. With this model, we can successfully explain reflection, refraction, and image formation in lenses and mirrors. But uh, this model we cannot use to explain the optical phenomena such as interference, diffraction, and polarization. In wave model, we consider light as waves. This model is successful in explaining interference, diffraction, and polarization of light. In this video, we will focus on the wave model of light, and you will learn about interference, diffraction, and polarization. There is another model that is a particle model. In this model, we consider light as particles. So this model is successful in explaining the interaction of light with atoms and electrons. So we start with the wavefront. So here I have a narrow beam of light. This light is from a laser. A laser produces monochromatic light. So the monochromatic means a single wavelength. We consider light as wave. So for this light, so I have this wave. So now you see here, this the peak of the wave is the crust. Now, if you draw a line that connect all the points on the crust, so I draw a line that connect all the points on the crust. So these lines are called wavefront. These wavefront are separated by a distance equal to the wavelength of the light. So when the light move, that when the light propagates, the wavefront also move with the light. So here I consider it as two-dimensional so that I can draw easily. So so this light beam is three-dimensional. So in three dimensions, so instead of straight lines, you will get planes. So we call this wave a plane wave. So lasers produce monochromatic plane waves. So a wavefront is all the points on a wave that form a wave crust. So now here I have a source and the wave coming from the source in different directions. Okay, these represent the wave in different points. Now, if you connect all the points on the crust, so you will get these circles. So these are the wave fronts for the this wave from the source. So these are the wave fronts. Also, you can draw more. So this is actually a picture that is two-dimensional, but actually in 3 dimension, the light is coming from the source in 360 degrees. So actually they form a sphere. So this wave is actually a spherical wave. So in 3 dimension, so actually these wave fronts are a spherical wavefront. So now you see here, these, if you put lines and they represent a plane wave, and if you put a circle, it represents spherical wave. So this arrow shows the direction of propagation. So here, so it will move in this direction. So that is the direction of propagation of the wave. So next is Huygens principle. So here I have a source of light, and so there is a spherical wave is from the source. And now, so this is a wavefront, and this is the next wavefront. So this wavefront will move forward with the speed of light. Now, so according to the Huygens principle, every point on a wavefront can be considered as a source of tiny wavelets that spread out in the forward direction at the speed of the wave itself. So it says that if you consider this wavefront, every point on this wavefront acts as a source of light. So they send out a spherical wave. They send out spherical wave like this source. But we call these wavelets, tiny wavelets. Now, to find the next wavefront or the new wavefront, you just take the envelope of these wavelets. So the new wavefront is the envelope of all the wavelets. So that is tangent to all of them. So this envelope of these wavelets is the new wavefront. Okay, so this Huygens principle has many applications, So for example, so here, diffraction. So first, what is a diffraction? So the diffraction is the bending of waves around the corners of an abstract. So here I am taking, so here I am considering a sharp edged object. Now, so from here I am sending out some light. So now, according to the ray model, so the light travels in straight lines. So here, these lights are blacked by this object, and but this light, so they go straight line. They go in straight lines. So you see here, there is no light here. No light. So there is no light here. So this is according to the ray model. So no light here. But actually, there is some light. Light in this shadow region. So there is some light. So you have light like this. So you see here, so this light actually bends at this corner. So this is called diffraction. So with the ray model, we cannot account for diffraction, but the wave model. So that means with the Huygens principle, we can explain diffraction. So here you see here. So this is a plane wave, and you see. So these are the wave fronts. So this wave front is moving, and here you see that there is a small hole, and the light is blacked here and also here. Now you see that this wavefront goes here. Now, so according to the Huygens principle, so the each point acts as a source. So now, so I consider some of the points. If you take this, so there is a wavelet here. There is another wavelet. So now, so the new wavefront is actually the envelope of this. So this is the new wavefront. So now each point on this acts as another source. So now they will have wavelets. That means they send out wavelets. So, and if you keep doing, so you can see that there is a light. So here and also here. So you can clearly see that. So this wavefront actually bend, and you have light in the shadow region. So this is according to the Huygens principle. So with the Huygens principle, we can explain diffraction, why there is light here. Next, we can prove with the Huygens principle that when light travels from one medium to another, its frequency does not change, but its wavelength and the speed changes. So here I take, this is the vacuum, and so there is a light, and its wavelength is lambda, and the speed is c, and the frequency f. So this is in vacuum. Now I consider a medium. So this is a medium. So with the refractive index n. So n is the refractive index of this medium. And here there is a wave. There is a light wave. So now, according to the Huygens principle, the frequency does not change. It means the frequency is same. So here and here. Now the wavelength, it changes. So I take this wavelength is n, lambda n. So that is the wavelength in this medium with refractive index n. Now the speed also changes. So the speed I take v. Now, so here, so you can write, so for this wave, c is equal to, so we use this equation, v is equal to f lambda. So here the velocity is c, so c is equal to f lambda. Now here, so the wavelength is lambda n, and the frequency is the same, f, and the speed is v. So here I can write v is equal to f lambda n. Now, so what I'm going to do is, so I divide this equation by this equation. So I will get c divided by v is equal to f lambda divided by f lambda n, and I can cancel f. So from this, I have c by v is equal to lambda divided by lambda n. So this c by v is actually n, because n is equal to c by v. So I can substitute n is equal to lambda divided by lambda n. So from this, I can get lambda n is equal to lambda divided by n. So you see that the lambda, here lambda is the wavelength of the light in vacuum, and lambda n is the wavelength of the same light in another medium with the refractive index n. So the wavelength decreases. So according to this equation. So next is interference. So the interference refers to the overlapping of two waves in space and time. So here, so I have two waves, wave 1 and wave 2. So you see here the crest of this wave and the crest of this wave, they overlap. So here you see that the crest of the two waves overlap. So here also the crest of the two waves overlap. So we call these two waves are in phase. So these two waves are in phase because the crest and crest overlaps. So now, so if you add these two, you will get the resultant. Now the amplitude of the resultant is actually the sum of the amplitude of the two waves. So you add this, add the amplitude of this wave and add the amplitude of this wave. So that will be the amplitude of the resultant. So this interference is called constructive interference. So the in a constructive interference, in-phase waves overlap. So and the resultant has the maximum amplitude. So in a constructive interference, you get a maximum light. Now you see here, so this is wave 1, this is wave 2 here. So this is the crust and this is the trough. So here the crust of this wave overlap with the trough of this wave. So also here the crust and the trough overlaps. Okay, the crust and the trough overlap. So here you see that these two waves are out of phase. So we call these two waves out of phase because the crust and the trough overlap. Now, so if you add these two, so you have nothing here. The resultant will be the minimum. Actually here, a minimum light. So this interference is called a destructive interference. So the destructive interference happens when out of phase waves overlap. So here the resultant amplitude. So what is the resultant of these two wave amplitude? So that is actually equal to the difference of the amplitudes of the two waves. So you take the amplitude of this wave and take this and take the difference between the two. That will be the amplitude of the resultant. But here it is a constructive interference. So here you need to add the amplitude. So here you take the difference, here destructive interference. So next is Young's double slit experiment. So Thomas Young in 1801 for the first time provide a convincing evidence for the wave nature of light. So he did an experiment. It is called Young's double slit experiment. It is a very famous experiment in physics. So he also measured the wavelength of light for the first time with his experiment. So if you can measure the wavelength of light, then it means so the light should be a wave. So if there is no wave, you cannot measure the wavelength. So Thomas Young so first proved that so the light is a wave. So now we will see, so what is that experiment? So here, this is the experiment, that is the Higgs double slit experiment. So you see here, there are two narrow slits. So there are two narrow slits, S1 and S2. Now there is a screen here. So this is a screen. So that is at a distance from these slits. Now here we are sending a monochromatic plane waves. Okay, so you see here, so this is the light we are sending. So this is a plane wave and also monochromatic. Okay, it is single wavelength. So now you see here, so at this and this slits, there is a diffraction. So due to the diffraction, you can see light here and here also. Now you see, so this light incident on the screen, and there is some fringes formed on the screen. So like this, so you can see there are bright and dark fringes formed on the screen. So now, if you take this, so this is the screen, and this is the center of the screen. So we take the distance between the screen and the slits is L. So you see here, so this center is at the same distance from here to here. So from here to here, and from here to here, the distance is the same. So it means if you consider a wave, so from this slit and a wave from this slit, so both travel same distance. So that means, so they interfere constructively at this point. So here there is a constructive interference. So because, so there is no path difference between the two waves. Path difference. So it means, so if you have one wave here and another wave, so they travel same distance. They start at the same point, at the same source, and they travel at the same distance. So it means, so they are in phase. So they should be in phase. So there is a constructive interference here at the center. So there is a bright spot here. So that is a bright fringe. So you can see at the center. So now, so I take another point here. So I take another point here. So we will see what is the fringe here. Is it a bright fringe or a dark fringe? So I take this angle theta. Okay, so for this one, I have this picture. So you see that S1 here, S2, and so D is the distance between the two slits. So here D is the slit separation. That is the distance between the two slits. So you see here, so this angle is theta, this angle. So that is this line you draw from the center of these two slits. So here, and to a point on the screen. So this is a screen. So now you see here, if you want to find, so the what fringe is here. Is it a dark or a bright fringe? So you need to know the path difference between the two waves. So this wave and this wave. So we need to find the path difference. That is the difference between the this length and this length. So now, so from the geometry, you can see that the path difference between these two waves is d sine theta. So d sine theta. So if this d sine theta, this path difference is 0, then there is a constructive interference. And you get a bright fringe. Okay, not only that, if d sine theta is equal to lambda, so then also you get a bright fringe. Also 2 lambda. So here lambda is the wavelength of the light. So if d sine theta is equal to 2 lambda, you will get the bright fringe. So in general, if d sine theta is equal to m times lambda, so you will get a constructive interference and you get a bright fringe. So you get a bright fringe. So this is a condition for constructive interference or the bright fringe. So here m is equal to 0, 1, 2, 3. So if you put m is equal to 0, actually that means there is no path difference. So that no path difference. So this corresponds to the center bright fringe. So that is the, so this fringe, the center. So you have the fringes like this. And the center is bright always. Because, so you saw here, the path difference is 0 at the center. So there is a bright fringe. Okay, so now if you put m is equal to 1, that is the first bright fringe. So you see here, this one, that is, so this, the center corresponds to m is equal to 0. So this is m is equal to 1, this is m is equal to 2, this is m equal to 3, and this is m equal to 4. So here also m is equal to 1. So on this side, so m equal to 2, m is equal to 3. So these are the order of fringes. Okay, so now, so if the path difference between the two waves from the slits is equal to m plus 1/2 times the wavelength, so you will get a destructive interference. So the destructive interference means, so that is a dark fringe. So this is a condition for dark fringe. So here m is equal to 0, 1, 2, 3. So if you put m is equal to 0, m equal to 0, that is actually the first dark fringe at m equal to 0, and m equal to 1 is the second dark fringe. So if you go here, so if you consider these are the bright fringes. In between, you have dark fringes. So you have, if this is a bright fringe, so here this is a m equal to 0. So that is the central. This is a central bright fringe. And here m is equal to 1. So that is a first order bright fringe. So here m is equal to 2. That is another second order bright fringe. So here, so you have m is equal to 1, m equal to 2. Okay, these are the bright fringes. But in between, so you have dark fringes. So this is actually the first dark fringe. No, not that one, this one. So this is the first dark fringe here. So just above the central bright fringe. So also this is also the first dark fringe. So here and in both sides. So the here one and here one. This is the second dark fringe here, and so on.